Um, so first of all, greetings to everyone. So in case I don't know where you are now, so I want to see good morning, good afternoon, and good night. So today it's my greatest pleasure to introduce one of the best scientists from Toronto, Jessica Burgner-Kahrs. Jessica is an associate professor at the University of Toronto, and she received her doctorate degree in computer science from Karlsruhe Institute of Technology. And before joining the University of Toronto in 2019, Jessica was an associate professor with Leibniz University, Hanover, Germany. And so as the topic says, Dr. Burgner-Kahrs, her research focuses on continuum robotics, and her fundamental robotic research is driven by applications in minimally invasive surgery and maintenance, repair, and operations. So her research was very well recognized in the robotic automation community, and she has won a number of prestigious awards. To name a few, the Heinz Mayer Leibniz Prize, the Engineering Science Prize, and the Lower Saxon Science Award. So I think I have to stop here, otherwise I will take up too much time. So she also was elected as one of the top 40 and 40 in the category Science and Society by the business magazine Capital. So without further ado, I would like to turn the mic to Jessica, and let's enjoy her fantastic talk on continuum robotics. Jessica, please.
Thank you so much for the kind introduction, John. I really appreciate it. It's quite an honor to give a keynote lecture at ICRA today, so I'm really excited to talk to you. I want to congratulate the organizers and contributors to the conference to really pulling off a fantastic program. I have been enjoying the start of the conference very much today, and I'm looking forward to the remainder of the conference. I'm a continuum roboticist, and I want to tell you about this exciting area of robotics research at the intersection of hyper-redundant and soft robotics. And I want to tell this story in 3 acts. I want to start with the history of continuum robotics research, and then move into the success story of continuum robotics in medicine. But then I want to exploit the unanswered questions in continuum robotics research and also take a step into the future with you all. So let's start with Act 1. Let's start with the history of continuum robotics. My history starts with Victor David Scheinman that we can see here. He died a few years ago at the age of 73. And he is really one of the robotics pioneers. He invented the Stanford robotic arm while he was a grad student at Stanford in 1969. He founded a company in 1973 to create the Puma robot, which is the industrial robot nowadays that has been used in so many industrial automation tasks. He later sold his company to Unimation, and everybody knows how that turned out to be in robotics. What many people don't know about Victor Scheinman is that while he was a grad student at Stanford, he also developed and invented the first continuum-style robot together with Larry Leifer, another graduate student there, in 1965, so even before the Puma robot. We can see the robot over here on that slide. It's called the Orm, which is Norwegian for snake, and it was pneumatically actuated. In terms of all these rubber sacks, it's 28 of those sandwiched in between 7 metal plates. And so this little robot could achieve bending in 2 degrees of freedom. Nowadays, the robot is on display in the Computer History Museum in Mountain View, California. If you ever happen to be there, have a look. It's a remarkable exhibition. Yet the Orm proved to be very difficult to control, right? It's a pneumatic actuated robot, and it was abandoned because movement could not be repeated accurately. That's at least also what the display says. So the robot was quite a contrast to the Puma robot. And before we move on with some of the historical view on continuum robotics, I want to quickly define what we understand as a continuum robot. A continuum robot is an actuatable structure whose constitutive materials forms curve with continuous tangent vectors. Continuum robots can bend, often extend and contract, and sometimes twist at any point along their structure. Now, I will show some robots today that are strictly speaking not continuum robots by this definition, but would be rather categorized as hyper-redundant robots. Yet, as their appearance is quasi-continuous, I'm going to include them. And the ORM was just one of them that is quasi-continuous. Now, with this in mind, let's look again to the history of continuum robotics. And on this slide, I'm trying to compile some of the pioneering work in the last century on continuum robotics. Another first, or like the second continuum robot is shown up here, developed by Anderson in 1967, using a cable-actuated continuum robot. Then we see some pioneering work, for example, by Hirose's lab in Japan, that he also not only pioneered snake robotics, but also continuum robotics. Here we can see the Elastor continuum robot using a spring backbone as well. And then we see a similar design picked up by Morecki, building this elephant trunk style inspired continuum robot. We can also see several more elephant type robots on that slide, as well as Wilson's first soft pneumatic continuum robot manipulator with multiple bending sections that he developed at Duke, even had a 2-finger soft gripper in the late 80s. And then some of the pioneering work from Walker and Rahn on the oct arm that many of us know very well has been a really a cool continuum robot that we have been seeing. Looking at that history, though, we can see that one thing is very common. The size of these continuum robots is very comparable to the industrial robot arms that have been developed at that time as well. Industry also picked up continuum robotics. Some companies took on these design paradigms. For example, Festo, they introduced their bionic handling assistant in 2010, which is showcased here. And also the latest version, more of a collaborative robot arm that we see down here is just a descendant of the first one. And these robots are also great showcases for bionic inspiration by the elephant trunk, and also great showcases for technical advancements that Festo made, for example, on pneumatic actuators, pneumatic control, and also additive manufacturing, as these bellow structures here were additively built. Yet the size and also the payload of this continuum robot really brings no significant advantage over conventional jointed robots. So it's a great showcase, but probably not that much more. OC Robotics also amazed us by building a very long cable-driven continuum robot, strictly a hyper-redundant robot. It's 5 meters long. The whole body is translated, as we can see, and 3 meters of that robot are actuated and can bend, as we can see on that clip here. Also a great showcase for continuum robotics paradigm. Yet also here, I fear that the benefit over conventional robots is not that major either. And so while in the last century, the third industrial revolution really kicked off in 1969 with the Puma robot and Unimation, serial robot arms are really characterized by repeatability, accuracy, payload, speed. As roboticists today, these are the 4 characteristics we mostly talk about. How accurate is the robot? How reliable is it? How fast is it? How much can it carry? And all of these are pretty much not the unique selling points of continuum robots. They are not known to be very repeatable, not very accurate, payload is pretty low, and they usually also move pretty slow. So when we conclude that history, we can see that all this exploratory continuum robotics research in the last century brought great advancements in terms of design, actuation, and modeling, yet continuum robotics really did not prove to have any superhuman capabilities. And so these large-scale continuum robots did not really bring a lot of benefit over typical robot applications in automation. And so continuum robotics pretty much stayed in a niche research area. Now, this low point in the history of continuum robotics research leads me to Act 2, where I'm going to talk about the medical success story of continuum robots. Also in the last century, the very first work on small-scale continuum robotics appeared in the literature in the late 80s, 90s. And I'm just showcasing 2 of these very remarkable works at that time that I found. on this slide, which also both originate from Hiros's research lab. On the left-hand side, we see an active endoscope that has been driven by SMA wires to build a very small continuum robot meant to sneak in hard-to-reach places on tortuous paths. And on the left-hand side, we see very small-scale soft-bodied pneumatic continuum robots. And with continuum robots becoming smaller in terms of their size and diameter, what became really apparent is that there may be a significant benefit over serial robot arms or industrial style robots in medicine. It was around the same time in the mid-80s when industrial robot arms were also explored for surgical robotics. The Puma robot arm itself was used in a neurosurgical example, which really pretty much kicked off surgical robotics. Yet in medicine, there's often the need for approaching any disease minimally invasively through a keyhole, trying to lead to shorter hospitalization, shorter recovery times for the patient. And rather than opening the body at large, making a large incision, physicians really prefer to make as small of an access as possible to reach these locations deep-seated within the human body where cancer might occur or any other disease. For example, deep-seated tumors within the brain that we may want to reach on nonlinear trajectories, or suspicious nodules within the lung, cancer in the urethra, at the kidneys, in the heart. All these applications or these medical scenarios have in common that they are very hard to reach locations somewhere within the human body. There are tortuous paths to overcome. And at the same time, we have to respect task and anatomical constraints. And so here, continuum robots prove to be very promising because their dexterous motion capabilities and their ability to reach more rather than being very accurate is actually quite interesting for these applications. And so that's also about that, about like 15 years ago, my personal journey in robotics started. I was a PhD student at Karlsruhe Institute of Technology working on surgical robotics. At the time, I used a Stäubli RX90 robot, a descendant of the Puma robot, for laser bone cutting in neurosurgery, which was great. It was the world's first autonomous bone cutting with a laser and a robot. But then in 2009, I believe it was at ICRA in Kobe, I was very intrigued by listening to a talk from Bob Webster that we can see here on that slide. He was talking about his continuum robotics research and how these could be used in medicine. And that very much intrigued me, and I joined his lab eventually as a postdoc in 2010. And that's pretty much when I started to become a continuum roboticist. The first continuum robot I focused my early career on was on the concentric tube continuum robot that many of us may know. For those who don't, I want to quickly tell you how it works. So it's the smallest of all continuum robots. You can see it's very small in terms of size. It can be up to 30 centimeters long and has a diameter of only 0.5 to 3 millimeters, like a medical needle at pretty much. And it's composed of several concentric tubes that are super elastic and nested inside of one another. And you can relatively translate and rotate those at their bases, and they will elastically interact, which defines the motion capabilities that we can see here and often referred to as almost like a tentacle-like motion behavior. And you may tell at this small scale, this continuum robot is predestined for medicine, right? It can pretty much achieve very many things within the human body at that needle size factor. And in the next couple of minutes, I want to spend some time and talk about 3 example projects in medicine that I have been working on that are characteristic for this success story of continuum robotics. Typically, surgical robotics research is top-down research. We talk to clinicians, have clinical collaborators that tell us what they would like to do better in surgery, what they can only hardly do today, or what is even impossible for them to do with tools. And then as surgical roboticists, we come in and say like, well, we can build you a robot that can probably do better, or can reach places that you may not be able to reach. And so when I started on continuum robotics in 2010, Caleb Rucker just finished his derivation of a geometrically exact model considering external loads on concentric tube continuum robots. And so we took his work and built on that. On top of that, we computed the kinematics and this kinetostatic model efficiently, derived the differential kinematics, facilitated teleoperation, worked on the human-machine interface, integrated it with image guidance, built this very nice dual-arm concentric tube continuum robot system. We tested it in vivo in a patient to show that you could reach the skull base through the nose to remove a tumor. And that was really exciting. Like there were a lot of firsts, a lot of fundamental contributions all at the same time. It was also around these years that I started off my work on computational design optimization on concentric tube robots. So there were all these firsts and we were really excited. And while this application at the skull base may have not been the one that concentric tube robots really are best for, it very much brought attention from a lot of physicians and clinicians to this type of robot. And so we happened to find a really promising area of concentric tube continuum robots in keyhole surgery. Here I'm showcasing some of the work we have been doing back then in neurosurgery, where a concentric tube robot could be used to enter into the brain through just a very small burr hole on the skull. Enter through this burr hole to remove, for example, a blood accumulation in treating a stroke patient by sucking out this blood. And that's what we see here with this intracerebral hemorrhage evacuation system that we have been building. Or one could use the concentric tube continuum robot to guide a laser fiber through the center and use that to ablate a malignant tumor right in the center of the brain, just through a tiny incision. So also here, our research was very much top down in terms of application. And we built this autoclavable actuation unit. We had the idea of maybe using simpler concentric tubes, but exchange the tubes in the surgery to achieve coverage. We further worked on design optimization. We looked at multiple competing objectives in how to choose the precurvatures of these tubes to have a certain motion behavior and reachability, which eventually led to the PhD of one of my first grad students, Josephine Grana. We developed algorithms for 3D volume coverage that may even go beyond applications in continuum robotics. And so that's really, it's really exciting, and it shows how top-down research and bottom-up research can go really hand in hand and lead to great advancements. And the third example I brought today is moving from the brain to laparoscopy, where we figured we could support single-site access surgery with continuum robots as well, because typically what you do in single incision surgery, you enter the abdomen through a single incision, for example, at the belly button, but usually you use a straight port and then you deploy instruments through this straight port. And so the idea that we had is using a continuum robot, so a continuously bending port, to enable the ad hoc reconfiguration of that port within the abdomen to change the viewpoint and also to change the access to the surgical site, for example, to remove a kidney tumor, as we can see here. And while this in itself is already a cool idea, we also worked on, can we then stiffen up that continuum robot to serve as a stable base? Because obviously deformation should not happen once you deploy additional continuum robotic instruments from that port to perform surgery. So the port features like these 3 channels for instruments to be then used through it. This work was pretty remarkable. It led to the PhD thesis of one of my other grad students, Erna Amanov, who also went into the operating room with all our clinicians to assess the requirements. They did laser scannings of the abdomen. They did probing of the inner organs to decide like what's distances, what the view angles that would be desired, and so on and so forth. So really exciting work showing how continuum robots could benefit surgery in multiple different disciplines. And so I could probably spend the remainder of this keynote talk and probably various other talks to just talk about all these various amazing research projects in continuum robotics in interventional and surgical applications. Some of them I feature here on this slide, which is unfortunately not exhaustive. I'm already sorry if I didn't feature your work on here or your favorite continuum robot in surgery. But you get the idea, like there has been so many great contributions within our field, exploring continuum robotics for all sorts of different applications in the human body to gain access to various locations. And while you may think that surgical robotics research in academia usually stays on the benchtop or doesn't go much further, in fact, continuum robotics successfully found its way into medical products over the past couple of years. And so that's really a huge success for that field. And I want to feature some of those clinically used continuum robots in the following. Here we see interventional continuum robots that many people may not think about as continuum robots, but steerable catheters, robotically steered catheters, are in fact continuum robots. They are long and limp continuum robots. They are only actuated at their tip. And so the environment, the vasculature, provides a tubular structure that is not much larger in diameter than the robot itself. And so by pushing and rotating it on the back and actuating the tip, we can pretty much steer through the vasculature to reach locations in the heart and in the brain to perform all sorts of interventions. And we can take this concept further, like ORIS, and build a robot for bronchoscopy, where you use the airways to reach into the lung for inspecting or taking a biopsy of suspicious nodules. And so this is great because it keeps the physician out of radiation. It improves the steering capability of these catheters and bronchoscopes, and allows us to use the teleoperation as a scheme for allowing the surgery to be more efficient. Now, as soon as we open, as we operate continuum robots in open spaces, we are more using different types of robot, not the limp ones, but the ones that can withstand their own weight. We see a couple of those here. One system is from Intuitive Surgery, also targeting this like single site surgery that we have seen earlier, where we did some work on the bendable endoport. Here we see the straight version of it. We also see Titan Medical's continuum robotic system for the single site laparoscopic surgery, which I believe is up for commercialization with Medtronic anytime soon. And then lastly, some more recent systems are those two here. On the left-hand side, we see Howie Joseph's company Robotics, where he took his pioneering work on snake robotics and found their way into the laryngeal area. So accessing the larynx or deeper through the mouth and using a continuum robot to deploy some instruments through there. And on the right-hand side, we see Bob Webster's startup company Virtuoso, where they are taking the concentric tube continuum robotic concept and proposing it for use in transurethral prostate surgery, which is, I think, now up for FDA approval. So we can probably conclude that second act of my keynote by stating that continuum robotics found a very compelling application area in medicine. And it's fair to say that the next generation of continuum robots in surgery will probably work hand in hand with surgeons, as we can see here. And it's a little bit tempting, I believe, to say that continuum robotics is purely medical or surgical robotics. And that brings me to the third act of this talk, where we're entering the climax, and where I want to take a step into the future with you all, and want to put a spotlight on the unexploited. I want to invite you to think outside of this medical surgical robotics box and see and think about what we may have overseen in terms of opportunity spaces. And I want to start this third act off with an example application that I have been thinking about. And it's a concrete example of where other domains that continuum robotics could be useful. And that is this on-wing jet engine inspection. We see here there are 3 technicians checking all the components of a jet engine on wing, using borescopes through very tiny access points to check hundreds of turbine blades on the inside for any issues. If they find an issue, they would take the engine off wing into full service and replace it. If they oversee an issue, we unfortunately may see it on the news. Happens from time to time. This is just a recent case where a United Airlines flight had to emergency land in Denver because the engine blew off. And now looking at this application, we can probably take our expertise from the surgical domain and keyhole access surgery to automate this process, to use a Continuum robot and automate the inspection, save time, save costs, save labor, add safety to this whole procedure by just having the Continuum robot do it autonomously. And when we start thinking about those, this outside of the surgical box domain, then a lot of applications reveal themselves that are characterized by similar requirements: limited accessibility, being in a highly constrained environment, needing to overcome tortuous paths, and the necessity to be able to manipulate once you reach a location where you'd found something that need to be repaired or need to be inspected closer. And so facilitating in situ non-destructive inspection of tubing, of pipes, of complex machinery is really huge in many markets, such as aerospace, nuclear energy, oil and gas, and chemical industry. Not needing to disassemble any of these machinery, not needing any of these hunched body postures, manual hour-long labor, and fiddling of manual tools or special purpose devices is really a great motivation for exploiting Continuum robotics further. And yet, moving outside of that domain that we know so well in Continuum robotics, the medical and surgical domain, we also have to think about the Continuum robot design again, because in medicine, we had to design Continuum robots that were, well, somewhat small, but also didn't need to be that long because the distances they had to overcome were not that large. Now, on the other hand, we need long and thin Continuum robots, which hasn't been looked at too much. We may have larger access points. We may be less restrictive in our material choices because biomedical compatibility, for example, is not that important anymore. So the design space becomes larger as we broaden the scope. And here on that slide, I'm just summarizing some of the major design paradigms that are existing today in Continuum robotics, where the bottom represents more the soft-bodied Continuum robots that use fluidic or pneumatic actuation or smart materials such as electroactive polymers or shape memory alloys. And on the top, we see the harder Continuum robots that use tendon, wires, or cables for actuation, the telescoping tube structure, or also recently we have seen eversion as a way to actuate Continuum robots. And so the challenges in researching long and thin Continuum robots are really that it's going to be important to solve how to maintain stability of our Continuum robot, avoid buckling over these long distances, and still have useful motion capabilities and steering while being able to bear a sufficient load. And so there has been some work, not much, only very few researchers have been looking into these long, thin Continuum robotics applications. And one of the important pioneers is clearly Ian Walker from Clemson University. He has been one of the first that built a very long Continuum robot that we see here. It's the tendril that they built together with NASA, which was 1.5 meters long and a tendon-driven spring design. They adopted it just recently and presented it at ICRA, I believe 2 years ago, as this tree concept where the robot has a variable topology and a telescoping structure at the same time. So they use tendon actuation and telescoping and also branching Continuum robots to provide support, which I believe is a very promising idea as we are exploring larger machinery for inspection and tasks. Also, very few researchers looked at in situ inspection and repair using Continuum robots. There has been a lot of progress been made in the scope of the EU project MIROB around Jindong and Dragos Saxinte from University of Nottingham, and also Kai Xiu's group at Shanghai Jiaotong University looked a little bit into Continuum robotics for these in situ inspection tasks. And we have also recently starting to see larger diameter Continuum robots making their way back into meaningful applications, as the Vine robots were proposed by Elliot Hawks and Alison Okamura in 2017 that we have all seen on the Science Robotics cover. So this growing eversion type continuum robot receives increasing attention in the past couple of years. This is just showing two examples, the Roboa from ETH Zurich, which is meant to do search and rescue operations using this eversion as an actuation principle. And also very recently seen some work from the German Aerospace Center where they built a continuum robot for fuel tank inspection. And so what is great about this eversion principle is that the robot has the ability to grow into an environment, to deploy into an environment without the need of translating the whole body, which I believe is really important as we are going to inspect partially unknown environments. And so our take on enabling extension and contraction in continuum robotics is by building a continuum robot that uses the best of two worlds. So we are using tendon actuation for the active steering of individual segments, but we are also utilizing the concentric tube paradigm in order to achieve variable length in those sections. And so an individual section is then composed of one tube that extends and contracts, where the end disc is affixed to. And we use tendons for inducing the bending motion. And then the tendon routing discs are composed of magnets at alternating polarity orientation, such that they always distribute equally and guarantee a good bending behavior. In these videos, we can see some of the 3-segment prototypes that we have been building by steering in 3D, by spatial steering, and also down here by performing a follow the leader motion. We have also recently started to explore that this a single segment can also achieve torsion as one of the motion paradigms we've been seeing earlier: extension, contraction, bending, and also torsion. And so now we have a robot that is able to achieve all of these motion paradigms in a decoupled fashion. And so this is really exciting. Yet in making this robot much longer, we will run into weight issues because the magnets and the tendon routing discs will increase the weight of the robot, and we will soon may have stability issues and buckling. And so we have been looking at how can we build a lighter weight, longer yet steerable structure, and have recently proposed this origami tendon-driven continuum robot at Robosoft, where the origami builds the sheath and also supplies the tendon routing, and the center is a concentric tube mechanism to allow for full extension and contraction of the segments. And while this is all really promising, we have also been scratching our head about the accuracy repeatability question that is really, as I mentioned earlier, not a unique selling point for continuum robots, yet we believe that we may overcome some of these limitations by combining tendon-driven continuum robots in parallel structures. And this has been a line of work that we have been starting about 3 years ago, where we have been looking into using tendon-driven continuum robots as the active components in parallel robots. Here we see planar and spatial designs. The spatial design is going to be presented in the Continuum Robotics 2 session later today by Sven Lilge. So join him to learn more about the robot that we're seeing here. And I go also much more into detail on our parallel tendon-driven continuum robot work in the Parallel Robots or Not Parallel Robots workshop on Friday, I believe. And so what's great about these parallel robots using tendon-driven continuum robots is that the tendon-driven continuum robot itself is very useful because it can individually actuate and move into a desirable workspace, as we can see a little bit here. And then they can be joined temporarily as parallel continuum robots to perform a task more accurate, more repeatable, and then move on as individual robots or move out as individual robots. And so talking about tendon-driven continuum robots, we have also taken on the endeavor last year to unify and formalize tendon-driven continuum robot models, as there are very many out there. And we created a guideline for the community, which is available on with open access on the Frontiers AI and Robotics journal. And we also released the code open source for all these models for the community to use as a gold standard to compare their results with. And I just want to quickly touch on the modeling aspects that are important to consider because we are looking at a continuously bending structure. There are multiple ways on how to go about how to represent the robot. There are we can differentiate between lump parameters and distributed parameters. And in the lump parameter paradigm, we can discretize the shape of the continuum robot and represent it by some finite number of parameters that we have some certain assumptions on. For example, the robot undergoes constant curvature, or there are no external loads. And then we can use this minimum parameter set or minimalized parameter set for kinematic and static modeling. You can join Priyanka Rao's talk in the Continuum Robotics 1 session later today to learn about Euler curves as an example of how to create a lump parameter representation that is very valid for continuum robots. The more parameters we include, we come to distributed parameters models where we use this state space vector as a continuous function with respect to arc lengths along the robot without making any assumptions on the backbone shape. So we have a geometrically exact model, and then we account for the arbitrary variations in the curvature of that robot by differential equations, and the change in state can then be fully specified by the rate of change in strain variables u and v. And you may tell the complexity of these models increases quite a bit the more descriptive they become. And so we could certainly try to include all the physics parameters, all the physical phenomena that this robot is undergoing, like friction, for example, or any of these aspects. Yet the model is complex and highly nonlinear. And if we want to be like computationally still able to cope with this in real time, we will soon need to find like a sweet spot. And the sweet spot we have been finding was the Koszrad-Rod theory in order to solve these models. And if we calibrate the model really well on a physical prototype, the rule of thumb today of these physics-based models is that we can achieve an accuracy observed at the tip of 1.5 to 3% with respect to the length of the robot. So the longer it gets, the worse it gets as well. Makes sense. Yet there's clearly room for improvement. And so we have been looking at using machine learning to overcome this complexity of the model and the high nonlinearity by just collecting data on the robot behavior. And there has been some really cool work by Reinhard Grassmann, PhD student in my lab. He has been looking at forward and inverse kinematics and has been showing that there can be significant improvements on the accuracy of the model. And also later today, in the session right after this keynote, Continuum Robotics 1, Nan Yan, a grad student in my lab, is also going to present on our recent work on inverse kinematics from shape to joint. And he shows that a learning-based model can outperform numerical inverse kinematics by far, which is very exciting. So that whole model inversion using learning is really exciting for control of continuum robots. And so continuum robot control is arguably not sufficiently explored today, in my understanding, because in the medical context, in the medical domain, we were good enough to focus on teleoperation most of the time. Physician stays into full control. We rely on the human in the loop. Human closes the loop. So many things have been easier because of that. But there's a huge opportunity space that's really not explored to its full extent, because now that we're moving out of that medical box, we can move towards more autonomy of continuum robots as well. And so there are exciting problems to solve, such as controlling the full body, its shape, its context with the environment. So many things to do, yet there are challenges inherent to continuum robot, which make these an exciting research area as well. So we are facing a nonlinear system as the number of kinematic degrees of freedom approaches infinity. We are also facing an under-actuated system. So it's impossible to actuate all these degrees of freedom independently and simultaneously, which makes it exciting to deal with as a control problem. And lastly, it's also an ill-observable system. So it's impossible to obtain sensor information on all these degrees of freedom. And on top of that, we may also have a very different sensor selection now that we're outside of this medical box. We may be less restricted, but we may also face new challenges because the workspace that robot is currently covering may be larger. And so covering that with sensing means may also be challenging. And I just want to give one example of underexploited areas in the control side of things, and that is redundancy. We can see on that slide some of our attempts and work on adapting null space projection methods and weighted damp least squares approaches to achieve secondary tasks by resolving the redundancy in the system. We see this 3-segment tendon-driven continuum robot with the extensible sections that I've been showing earlier here, performing a task, position controlled. On the left, we see it circling a path, and here we see it deploy along a path. And as a secondary task in this weighted damp least squares approach, we are enforcing additional constraints on the shape that we envision with this green sphere here. So the robot is not supposed to move its shape away from that constraint. And so while these conventional approaches adapted into continuum robotics work reasonably well, I believe that there needs to be more thought into exploring and formalizing the redundancy that is in continuum robotic systems, because it's a continuous bending structure in terms of its shape. So there could be more to it than what we can exploit right now on the surface. And that is really exciting. And moving even one step further, I think it's also important that as we think about these continuum robots to deploy into unknown or partially unknown environments with or without a digital twin, there is so much room to exploit morphology and collaboration of these robots. So we may not only rely on these actuatable degrees of freedom, but we may want to exploit the embodied intelligence in the system, the inherent compliance in the system. We may want to purposefully interact with the environment and purposefully make contact with the environment for steering. And probably also, rather than focusing on coming up with this one Swiss Army knife, long and thin continuum robot, we may want to think about having multiple continuum robots collaborate with each other to attain a certain task. And with that, we can then see that by entering through multiple entry points and supporting each other, we can see that what we learned inside that medical surgical box in terms of keyhole access serves as a great inspiration for the future of continuum robotics. This multiple arm collaboration on tortuous paths and coordination of their manipulation can really take continuum robotics to the next level. And I'm convinced that continuum robotics has not yet reached its peak. There's so much more to explore. And with that, I would like to conclude the keynote by taking you a step even further into the future of continuum robotics. And while we watch this last video clip, I want you to think about what continuum robotics could do in your domain. With that, I conclude this keynote talk. Let's all think out of the box. I want to quickly thank the brilliant minds that I have been fortunate enough to work with, some of which you can see on the slide and you have been seeing throughout the talk. It is really our collective dedication and passion for continuum robotics that brought this vision forward. I want to thank the funding agencies. I also want to thank the University of Toronto and the Robotics Institute for being such a remarkable academic home for us. I want to also quickly note that we are currently searching for another postdoc to join the lab soon. I will also hire at least 2 more PhD students in 2022 in computer science or mechanical engineering. So apply in the fall if you're interested. And I want to invite you all to collaborate with us and shape the future of continuum robotics with us. Thank you for your attention.
Thank you, Jessica, for such a wonderful talk. I want to back up Jessica's advertisement. The University of Toronto is one of the greatest universities. So I think if you wanted to do research in continuum robots, I think Jessica's lab probably is one of the best choice. To Jessica, for your information, so the attendees for this keynote session is not just like around 70 people. So in addition to our Zoom attendees, more than 4,000 people are watching this keynote talk on Bilibili website. So you're quite popular. So let's move on to this Q&A session. So you have two ways to ask a question. One way is you can raise your hand on the Zoom. I will allow you to use voice to chat. And the other one is you can just type in the chat for your question. So our first question is that, so it says, thank you, Professor. I have a question that except the surgical field, do you think that exists another good application for continuum robotics, both the large and minimal scale?
Yeah, I believe I answered the question probably after the question was posed, right? I believe there are so many applications in like non-destructive inspection, maintenance, repair, and operations. And as you have seen on the last video, who knows where continuum robots might end up? They might end up also in space sometime.
Yeah, so I think for industrial applications, continuum robotics also has a good area to explore. So the second question on Zoom is that I have a question about the design and the user design side. So what kinds of a robot or teleoperated interface design do you think are the most advantages for surgeons or other repair workers?
Yeah, that's a really good question. And also one of these areas that I feel is very underexploited today. There is huge potential for research in this regard. So far, we have been pretty much relying on the teleoperation interfaces that have been in surgical robotics, have been very prevalent. Like I think one of the most remarkable ones is probably the one of Da Vinci surgical system, right? The console and the user interface is just really intuitive. And so we have been relying on this in surgical robotics quite a bit. But when you now think about repair workers or technicians, for example, using these robots to inspect a jet engine, then the question becomes like, how do we also attain that shared autonomy, right? I foresee these robots doing a lot of the inspection autonomously and maybe just informing a technician about something suspicious that the technician could probably jump in and check or do some minor repair in a teleoperated fashion. And so then it is probably still relying on operating the tip, looking through a camera, providing that view into the system, but how that interface needs to look like, whether it should have haptic feedback, what kind of feedback it should have, how we would feedback information about the shape of the robot, maybe also whether it's having heavy contact with the environment and if something happens along its length. I have no idea, but I'm excited about these kind of questions and think that's going to be really worthwhile exploring. So thank you for asking the question.
Okay, our third question is about the continuum actuated parallel robots. So given the concerns on the repeatability and accuracy of a continuum actuation, so could you elaborate where the hybrid robots are preferred over the rigid counterparts?
Yeah, that's a great question. Like we just started that work 3 years ago, but we believe that these parallel continuum robot structures are much more lighter in terms of their weight. So that's one advantage that we can have. And one thing that I wasn't able to touch on in this talk very much, but briefly touched on at the end, is like these individual tendon-driven continuum robots can serve as individual robots entering on individual pathways. And so at some point they would connect to a parallel structure. And I think in this reconfigurability and in this ability to use these active links by themselves, there lies huge potential for these inspection applications and stuff. So it's an ad hoc build parallel continuum robot that can then move out of this parallel structure into serial structures again. I think that's where a huge potential lies.
Cool. So we have two more scholars from the audience want to talk to answer the questions. So I will first allow the Casper to talk. Hey, Casper, can you?
Yep. Hi, I hope you can hear me. Casper here. Hi, Jessica. Fantastic talk. Fantastic. I'm very happy that you showed your magnetic disk continuum robot, which I really like. I think you presented it first time. That's when I saw it in Hamlin, at the Hamlin Symposium a few years back. And I see also the problems because it is a heavy thing if it's too long. Another issue I can see is if you might go into an engine made of metal, you might get stuck to the walls. Is that an issue you have thought about or have a solution for?
Yeah, of course. Like, I mean, ferromagnetic material should not be present. But we haven't seen any issues with the jet engine yet. But for sure, yeah, the magnetic actuation may not be the preferable choice in some of these inspection tasks if we happen to be around material that would interfere with magnets. Yeah. Okay, could I just maybe extend from that? Yeah, I'm still on there. So thanks for the answer there. I also like your new origami style robots. I couldn't see what payloads they have, but I would think the payload is quite low, especially for some industrial applications. What is your view on that? Yeah, I mean, generally payload is not the unique selling point of Continuum robots, as I mentioned earlier, right? So for that origami style robot, the structure itself is very lightweight. As we rely on these concentric tubes in the center, they would pretty much make up the stiffness of the system and would define the payload. It may not be large, but I think as a first step, the visual inspection of any of the machinery or tubing or pipes is foremost important. And to me, the ability to then maybe repair something comes second. So that's why we were exploring that lightweight long structure first. But for sure, the community will need to think about ways on how to provide sufficient payload at the tip. And so I have seen there has been, we always have to find that balance of having great steerability, great bending capabilities of these systems, while at the same time not being so stiff and not having so reduced steering that we can reach far into a system. And I believe a lot of the work on variable stiffness materials and actively changing the stiffness of a system that will come in very handy and will be important that we join forces in order to overcome this challenge. Thanks a lot. Thank you, Casper. Thank you.
So we have another audience who want to ask. So Orange Salesman, I will let you talk.
Can you hear me?
Yes.
So first of all, thanks, Jessica, for the really inspiring talk. It's amazing work. You talked a lot about increasing autonomous capabilities, but in the talk, you kind of stopped at the control level and discussed advanced control capabilities when compared to the medical domains. Can you share your thoughts about higher level planning and not only control issues that will be challenges for these types of systems?
Yeah, for sure. I haven't touched on any of these autonomous behaviors because that's really not the expertise of the Continuum Robotics Lab that I direct. Like, we pretty much work on design, modeling, control, some motion planning, but that's pretty much our expertise. So in making more higher levels of autonomy possible, we would really rely on our collaborators. And I'm actively shouting out to the world if you want to join forces. And so that is going to be a whole different level. But I guess we as a robotics community can share our knowledge here because I bet there has been so much advancements in that field that I feel we can benefit from each other.
And if I may, another follow-up question. So again, in terms of planning, I know in medical applications, a lot of necessity is to have certifiable planners in terms of safety, in terms of bounded planning time. Do you think in these other applications, you will need theoretical guarantees on the quality of the solutions, or more ad hoc solutions are going to be what these applications are looking for?
Well, I believe that the safe answer is to say it depends on the application. No, but more serious. I think the benefit that we'll have here is that many of these machinery, tubing, whatever it is we want to inspect or repair, so we have that digital twin available to us, right? And so we can probably do a lot of offline planning to start off with. There may, of course, be things that we encounter that is not foreseeable, or there may be applications like search and rescue where it's totally unknown. But I believe that there's a great synergy. And I believe that some of those guarantees would need to be made in those application areas where safety is really at the forefront. Like if I would want to guarantee a Continuum robot to do a certifiable jet engine inspection, that I would like passengers to get on that airplane after without the engine blowing off. Yeah, for sure. So yeah, I guess that my answer pretty much shows that's an area that we all need to move in, and where it's going to be challenging to solve these issues.
Great, thank you very much.
Thank you for your question, Oren.
Maybe let's also use the last 3 minutes to answer one more question. It's also about the control problem from Professor Russell Taylor. So he's for the control. Can you see something about possibly low the rate to update from imaging and external sensors?
Yeah, for sure. Thanks for your question, Russ. Great to see you in the audience. Yeah, that's definitely right. The lower level control will always be faster as whatever the update rates are that we get from whatever sensors we're going to deploy. I guess, moving forward, we can certainly make use of all the control experience in general robotics where these issues have been on the forefront as well. It will always be that combination of different sensors, different sensor information at different times that will need to be used in order to make sure that the robot does what we hope it would in an autonomous or semi-autonomous fashion.
Yeah, thank you for your answer. So for those keynote, so for such a good keynote talk, the time always so short. But I think we have to end it here because of the other sessions will be started at 1. So lastly, please join me to thank you, Jessica, for such a wonderful talk. Thank you, Jessica.
Thank you, everyone, for joining today. I appreciate it.